Nick Lockwood, our new speaker. Welcome, Nick.
Bonjour, je m'appelle Nick. My name's Nick Lockwood. I'm an iOS engineer in London working with Schibsted. And I'm here to talk to you today about parsing formal languages with Swift. So what are formal languages? A formal language is text specifically designed to be read and possibly written by a machine. It's basically the opposite of natural languages, which Matt talked about yesterday. So examples would be any kind of markup or programming or data serialization language, things like XML, JSON, and so on. And of course, any programming language as well, like Swift C. So why would we want to parse formal languages, and why would we want to do it ourselves with Swift? Can't we just use a library? So for well-known formats and languages, of course you can use libraries, there are libraries out there. If you want to parse something maybe a bit more obscure, you might find that you're the first person who's trying to do this with Swift. And of course, for every language, somebody had to write the first implementation. So it's a useful skill to have. You may also want to create your own languages, custom DSLs, something that solves a problem that only you have. Okay, but isn't it easier to use a scripting language like Python or Ruby, something designed for text processing? It might be easier, but these languages are a lot slower than Swift. And also, Swift's strong typing is a really nice tool when you're trying to write a parser. But isn't Swift horrible for text processing? Well, it can be, depending on what you're trying to do. As it happens, for writing a parser, it's actually fine. Its kind of string interface doesn't cause us any problems. And the other good question is, well, why wouldn't you use a parser generator? So there are tools out there, code that can write code that will generate a parser for you from a set of instructions. And parser generators can be fun to play with, but even a naive hand-coded parser is going to be faster, easier to maintain, and probably produce better error messages than a parser generator. That might seem like a controversial statement, but you don't have to take it from me. You can take it from Slava Pestov on the Swift compiler team, who I think knows what he's talking about. So there's many different kinds of parser. There's been thousands of hours of research put into parsers. People have written PhDs about them. There's all these different formal academic terms. The good news is you don't need to care about any of that, because the only kind of parser that really matters that you need to learn about is recursive descent parsers. Now, this again may seem like a bit of a controversial statement, but you don't have to take it from me. You can take it from Doug Greger on the Swift compiler team. He says, don't let any PhD tell you otherwise, and he has a PhD. So. Okay, so recursive descent parsers. A recursive descent parser is a kind of top-down parser, which there are also bottom-up parsers. So a top-down parser works by taking a high-level construct in your language, so something like a statement, and trying to match that against your input text. And if it fails, it moves on to the next pattern and so on. And it does that in a predictable order, which is important. To demonstrate how parsers work, I've created a very simple example language. I don't have a name for it yet. It just has two kinds of statement, a declaration, where you say let some variable equal some value, and a print statement, so print a value. And it also lets you do some maths. You can add numbers together, and you can concatenate strings. So there's two stages to parsing. The first stage is lexical analysis, also known as lexing or tokenizing. And that's where you break your input text into individual words. Now, again, Matt talked about this yesterday in the context of natural language processing. It's the same idea, but here the definition of words is specific to our custom language that we've created. So there's no built-in library, built-in framework to do this for you. The next stage of parsing is syntax analysis, which is often what's colloquially called parsing. And that's where you arrange those tokens into meaningful statements. So let's look at lexical analysis. So first we need to identify the tokens that make up our toy language. I've put these into categories. So you have keywords like let and print, operators like plus and equals, an identifier, which is a letter followed by 0 or more letters or numbers. And I've kind of specified these using regular expression syntax, which some of you may be familiar with. Again, like numbers, just a digit, 0 to 9, or a decimal point. Strings are a quote followed by 0 or more non-quote characters and then a closing quote. And that's a very simplified string pattern. It doesn't attempt to handle things like escaped quotes inside the string. So how do we represent a token in Swift? Well, Swift's enums are perfect for this because they have this powerful feature where they can contain a sort of tagged value. So we have simple cases like the assign and plus operators, where they don't have any associated data. But then you've got things like identifiers, which have a name, numbers, which have a numeric value, and so on. And to actually implement Alexa in Swift, there are some built-in APIs in Foundation that look like they might be useful. The one you're probably most familiar with is the components separated by method on string. And that's really good if you've got something like a comma-delimited list, or maybe you want to split a file into individual lines. It's not so good when you have something more complex, like let's say we tried to tokenize our string by splitting on space. If we hit a string literal, which is like a quoted string, and that has a space inside it, you're going to end up splitting it down the middle, and then you've got like half a token on either side. That's not really going to work. The next option would be to use NSScanner. NSScanner is really good if you've got some input in a known format. So you have something like a string, and then maybe a number, and then another string, and then a date. But if you've got a sequence of kind of like any possible token in any possible order, scanner's not going to be that useful either. So the next option is NSRegular expression. Now, not everyone is a fan of regular expressions. I actually quite like them, but yeah, they're not everybody's favorite. But as it happens, when you're trying to write Alexa, regular expressions are kind of the right tool for the job in many ways. You know, a token is a non-recursive sequence of characters in a particular format. And that's really what regular expressions were designed for matching. So if we try and define our tokens using regular expressions in Swift syntax, we end up with something like this. And we've got a token for white space, because even though we don't care about it, we still need to recognize it so we can ignore it. And you know, assign and plus and so on all look very much like my token definitions from before. The pattern for matching a string is not so nice, and we run into a problem here that, unfortunately, you're trying to match like a double backslash in regular expression syntax where backslashes have to be escaped with a backslash, and then you've got to wrap that in a string where backslashes have to be escaped with a backslash, and you kind of end up with backslashception. So that's kind of one problem with using regular expressions for this. Another problem is that the NSRegular expression API has not really been Swiftified very nicely, and it returns all of its results using NSRange. And NSRange is a range of UTF-16 characters. It's what NSString uses. And those have no correlation whatsoever to the indexes in Swift string for reasons that Matt talked about yesterday. So you have to do a conversion back and forth, and it's kind of tedious. I don't expect you to read this function. That is the function that will do the job for you, but it wasn't very nice to write it. So lexing with regular expressions works, but it kind of sucks. So what's the alternative? Well, the alternative is to do it ourselves, character by character. So time for some string theory. I won't go into this in too much depth because Matt covered it very nicely yesterday. But yeah, a string in Swift is not a simple data structure. It's an abstraction. And there are several levels of abstraction you can choose to use called views of the underlying data. So at the top level, you have string, which is a collection of characters. And a character is a grapheme cluster. It's basically one or more related characters that make up a thing that you actually see on the screen. And that's kind of too high a level for what we want to do, for a couple of reasons. One is that we're going to use NS character set for matching our characters, and that really deals with code points like individual Unicode scalars rather than whole characters. And the other reason, it's actually a bit slower to use string than it is to use Unicode scalar view, which is the view underneath, just because Swift has to do more work to kind of like build those character clusters. The other thing is, as you're probably aware, in Swift 4, I think it was, Apple added this concept of a substring, which is a slice, a string slice. And this is useful because when we're going to be parsing our input, we have to keep track of two things. We need a reference to the input string itself, and then we need our current position in the string, where we've got to, the index. And substring nicely encapsulates both of these things in a single type so that we don't have to keep track of the index ourselves. So let's write some code. This is the tokenize function, which is going to do the lexing. So this takes an input string, and it throws an exception, which I'll talk about in a minute. And the first thing it needs to do is it takes that input string, gets a substring from it, and then gets the Unicode scalar view, which is what we're going to be working with. And I've created an extension on substring.unicode scalar view, which I'll talk about in a minute. So the next thing we need to do is chomp through our string and grab all of the tokens. And to do that, I'm calling this method readToken repeatedly, and it returns an optional token. So when it returns nil, that's when I've reached the end of the input, basically. And that's been implemented as a mutating method on substring.unicode scalar view. The reason it's a mutating method is not because it's actually changing the string, which I don't want to do because it would be very expensive to keep reallocating. All it's actually mutating is just the index, the start index of the substring, which is the slice. So it's just going to, every time you call it, it increments the index so that the next time you call it, it's already in the right place. And we keep calling that over and over again until it returns nil. And when it returns nil, if our input isn't empty, like if there's still characters left, that basically tells us that there's a syntax error. So there's some garbage in our input that isn't any recognizable token, must be an error, must be a user error. So we throw an exception. Otherwise, we return the tokens, and we're done. So how does the readToken method actually work? So the first thing that we need to do when we read a token is skip over whitespace. This is a whitespace agnostic language. We don't care about whitespace, but we do need to kind of ignore it. So I've got the skip whitespace function. It's pretty straightforward. It just repeatedly looks at the first character in the input. If it matches the whitespace in new lines character set, it removes it and keeps going. And when it finds something which isn't whitespace, it's done. And all of, to match my actual tokens, I've written separate methods. You could do this all in one giant switch statement, but I think it would be very hard to read. So instead, I've created separate methods to read each type of token. And I'm calling those in a chain using the null coalescing operator, the double question mark. So basically, that's, if the first one passes, the next one doesn't get called. This is quite a nice, concise way of writing the code. One gotcha to watch out for is that, at least in some versions of the Swift compiler, there's sort of a bug where if you have long expressions with lots of chained double question mark operators, it can sort of take exponentially long to compile. So if you have more than about 4 of these, you probably want to split that into individual if statements. It doesn't affect runtime performance, it's just a compile time issue. Okay, so let's look at read operator. So this is the actual sort of tokenization process. We pop the first character, check to see whether it's an equals or a plus, and return the appropriate token. And if it's neither of those, it's not an operator, so we return nil. And then the next kind of token method will get its chance to see if it matches. One thing worth noting here is I've assigned the value of self to a temporary variable called start, and then I'm putting it back again if I haven't matched any token. The reason I'm doing that is because pop first, which I'm doing in my switch statement, is going to move the index, the start index of the string along. And if I haven't matched anything, I need to move it back again so that the next token reading method can sort of start in the right place. Otherwise, I'm going to lose something. That might seem like it's inefficient, but remember, I'm working on a slice here. So really all that's doing is incrementing the index. There's no string being like, churned in the background there. There are different ways you could write this. So I could check, I could use first to look at the token before I move the index along. It doesn't really make any difference performance-wise, whatever's easiest. Okay, so let's look at the read identifier method. This is slightly more complicated. As I said before, an identifier in this language is a letter followed by 0 or more alphanumerics. So that's reflected in the function. You've got a method at the top to check whether the first character is a letter using the letters character set. If it's not, we return nil, because whatever this is, it's not an identifier. And if it is, then we keep looking to see if there's any more letters or numbers afterwards, and we append those to the resultant name. And then when we've matched the entire identifier, we do a switch on it to see if it matches any of our keywords. So it might be a keyword. If it's not a keyword, then it's just a user variable. Now, you notice I've basically combined several different kinds of token into this single read identifier method. You could split this up however you wanted. The reason I've done it this way is because if I had a separate method called like read keyword, and it matched, say, let, and then there was another letter after it, it would have to say, oh, actually, this isn't a let, this is an identifier, but that's not my responsibility. So we'd have to backtrack all the way back to the beginning of let, and then let the read identifier method handle it. And that's quite inefficient. That's in parsing, that's called backtracking, and basically the more backtracking you do, the slower your parser will be. So it's not sort of terribly critical to backtrack one character or so, but if you can reduce it by the design of your lexer, you'll have a fast system overall. And then this is the read string method, which is kind of complicated, and I won't go through it in detail, but I just wanted to include this to contrast with that horrible regular expression we had earlier. So this is some code that does the same job, but it's a lot easier to read and maintain. You can kind of follow what it's doing. It's going along, looking for backslashes, and then setting a flag to say that the next character should be escaped. I find that this is much easier to work with than a regular expression for this kind of purpose. And here's how we use our tokenizer. So you just call tokenize on your input string, and it's going to return an array of tokens. Very straightforward. So the next step is syntax analysis. So the tokenizer produces a flat array of tokens. That's the output of lexical analysis. Syntax analysis, however, can produce a hierarchical structure. And that hierarchical structure is called an AST, an abstract syntax tree. So the AST is made up of nodes. And so just like we identified the tokens for our language, we need to identify the AST nodes for our language. So the nodes are the high-level statements, like we have a declaration, which is let, followed by an identifier, followed by equals, followed by an expression. And we have a print statement, which is print, followed by an expression. And then an expression can be either an operand, so a number, a string, or an identifier, or it can be an operand plus another expression. So the expression node is actually recursive. It can contain other expressions. So to implement this, a lot of parsers would use polymorphism, so they'd have like a base AST node type, and then they'd have concrete subclasses of that to represent all the different kinds of node. But in Swift, we have these brilliant enums that we can just use again for the same purpose. And this is much nicer because they're strongly typed. We can do exhaustive switching over them, so we don't have to kind of handle the else case where you've got some sort of a kind of node that you don't actually know how to deal with. And again, here we have an enum, which is a statement, which is our top-level declarations. So we have a declaration or a print statement. And then each of those can contain a nested expression enum. And that can be either an operand, a number, string, variable, or it can be an addition containing two other expressions, a left-hand side and a right-hand side. Notice the use of the indirect keyword on the expression enum. If you've not seen that before, indirect is necessary when you have a recursive enum, so an enum that contains itself. And that's because enums are value types. So if you have a value type that contains itself, you basically end up with an infinitely large structure, which isn't possible. So that tells Swift that it needs to, the reference to expression internally has to be done by reference rather than by value. It makes no difference to how you use it. It's just an implementation detail. To write our parse function, it's going to be very similar to the tokenize function we wrote earlier. So it takes an input string. The first thing it does is call tokenize to actually get the tokens. And then it converts that array of tokens into an array slice so that we can use the same trick we used before with moving the index along. The next part is, again, exactly the same. So we chomp through. This time, instead of reading tokens from a string, we're reading statements from a token array. But the result is the same. We append those onto our statements array. We do that using a mutating function on the array slice itself. And then at the end, if we have any tokens left over, that's the unexpected token error situation that you've probably encountered before when you've mistyped something. So again, a lot of parallels with the way that the Lexa works. How does read statement work? Again, very similar to read token. We don't have to skip over whitespace this time because we already stripped all of that out at the lexing stage. So we just call read declaration, and if that returns nil, we call read print statement. I've shown the implementation of read print statement here, just so you can see what that's actually doing. So it's just grabbing the first token. If it's print, then it knows it's a print statement, and it goes on to read the expression. And if it's not, then it returns nil because this wasn't a print statement. And read declaration would work the same way, but I won't go through that. Read expression is a bit more interesting. So this is another method that we write. So read expression, first it needs to read an operand to see if this is an expression at all. If there's no operand, so an operand, remember, is a string, a number, or a variable, it will return nil. If there is an operand, it needs to check if there's a plus afterwards, because if there is, there could be more to the expression. So if there's a plus, then it calls itself again, recursively, read expression, to grab the rest of the expression. And because that's recursive, it could be arbitrarily long. So it could be A plus B plus C plus D, and so on. And then it returns the addition type expression in that situation. And then the read operand method that was called by read expression there's again, very similar design to the read operator we had in our tokenizer. It's just looking at the first token to see what it is. Is it a variable? Is it a number? Is it a string? And then it returns the appropriate expression type. And we use the parser in the same way we use the tokenizer. So we call it on a string, and it returns, if it's successful, an array of statements which can contain nested expression nodes. So that's basically our tree. We could have like a root node if we wanted, but it doesn't really give us any value. And if it fails, we'll get an error thrown. So now that we have an AST, like, what can we do with that? What's that useful for? Well, you can write a whole bunch of tooling on top of an AST. You can write something like a formatter or a pretty printer, write static code analysis tools. You can write an interpreter that will actually execute the program and give you the result. Or you could even write a compiler or a transpiler that turns it into machine code or another language like Swift, which could then be compiled. Just to give you an example, this is a formatter written for this toy language. This is 30 lines of code, and it fits on one slide. Very straightforward. And here's an interpreter that will execute the program and give you the output. This is 50 lines of code, and it fits on 1.5 slides. I won't go through it in detail, but you can see it later. So are there any enhancements we can make to this parser now that we've written it? Well, an obvious extension to our language would be to add more operators in addition to the plus that we have already. And we could also stand to improve our error reporting system a little bit. So if we wanted to add a multiplication operator, how would we go about that? So to extend the lexer, very straightforward, you just add another token type, which is times, and you extend the read operator method in the tokenizer to handle the times case. Extending the parser is similar, so we extend our expression enum in the parser to have a multiplication case there at the bottom. And that looks a lot like the addition case. So how do we actually implement that in the parser? This was our original read expression with a bit of padding in it. And it's reading an operand followed by plus, followed by another expression. And I'm going to modify that to instead of reading a plus, it will read a token, and then it will switch on the token to see whether it was a plus, a times, or something else. If it's something else, it's not an expression. If it's a plus or times, then it's either an addition or a multiplication. I call this a naive implementation because there's a slight problem with it. And that problem is operator precedence. So the way that this parser works is naturally right associative. What that means is if you have an expression like b plus c plus d, that gets treated as b plus c plus d. And that's fine when you have operators that all have equal precedence or are all the same. But when you have an operator like times, which has a naturally higher precedence than plus, it's a problem because b times c plus d should be treated as b times c plus d, but is actually being treated as b times c plus d. The precedence is wrong. So the solution to that is that we actually need, instead of treating just plus and times as expressions on an equal footing, we need to treat them as different kinds of node. And there's actually a nice term for this in algebra called a term. And a term is basically either an operand, like a variable, or it's two operands multiplied together. So we can add a term node to our AST. And so instead of just an operand and an expression, we now have a term, which is an operand times another term, and then an expression becomes a term or a term plus another expression. And the order in which I've defined these, or rather the order in which I process them in the code, is important. So I can extend my read expression method. Instead of calling read operand at the top now, it's going to call read term, and then read term has exactly the same structure as read expression, but it's looking for a times type expression instead of a plus type expression. And the precedence of the operators is now naturally baked into my parser. It's hard-coded into the parser because it tries to read a term first. It's the first thing that read expression does, before it tries to read an addition. And baking the operator precedence into your parser like that is fine when you know like all the operators at parsing time. It's like if you have hard-coded operators in your language. But in a language like Swift that supports user-defined operators, that's not going to work. And the way that the Swift parser handles this is it basically, when it reads an expression, it just puts all of the operators and operands into a flat array, and then once later it's gathered all of the user-defined operators, it can then recursively go through that array and work out what the actual sort of sub-expression should be. So the next thing to do is to improve our error reporting. So the problem with the way that we're handling errors at the moment is it's fine in the lexer because when we hit an error, we know where we are in the string, and so we can report like the line number where that error happened. But if we parse all the tokens successfully, and then in the parsing stage, we hit an unexpected token, you've used an equals when you should have had a plus, we can say that you've used the wrong token, but we can't tell you where in your source code that problem happened because we no longer have that information. So the solution is, instead of using a raw enum for our tokens, what we can do is we can use an enum for the token type, but then put that inside a struct and include the source string range in the struct as well, so that later in our parser, when we hit an unexpected token, we can map that back to the original source and say, oh, this was on line number 4. The other improvement we can make is, right now, if we say start processing a string and there's no closing quote, all we can really say is, okay, I have no idea what this whole thing was because it wasn't a string. But actually, we know that it was a string and we were just expecting a missing closing quote. So if we reported that error in the read string method, instead of just waiting till the end to see if there was any stuff left over, we could give a much more specific error message. Now, one way to do that would be to make the read token method throw an error, and we could just throw the error when we encounter it and make that error very specific, and that's good. But what would be even better is if, there might be multiple errors in our source code, and it would be helpful to the user to report them all at once rather than making them do a recompile cycle every time they fix an error until they're all gone. So if instead we added an error case to our token type, then we can return an error just the same way as return any other kind of token, and you can have an array of mixed tokens and errors, which can then be handled later, and all of those errors can be reported together. Okay, so that's everything I had to talk about today. Thank you for listening.
Thank you.
If you found any of this interesting, you can contact me on Twitter and talk to me about it. The code for this presentation, so all the source code and the slides, can be found on my GitHub repository here. And also, if you want to read more about how parsers can be written in Swift, I've got a blog post about how I wrote Swift format, which uses this same approach. And I have a library called Expression, which handles the custom operator case, where you can have user-defined operators as well. And finally, I mentioned right at the beginning that parser generators are fun to play with, but a waste of time. Well, I like doing fun things that are a waste of time, so I've written a parser generator in Swift, and if you'd like to look at that, that's the bottom link. All right, thank you.
Thank you. We'll ask Sam and Simone to join us. Thank you. That was one of the first questions. Good resources to go deeper. Okay, thank you, gentlemen, for your 2 talks. I was wondering, I get the feeling that Trill is really something that you can use to learn and to understand more how language work. Is that its only goal?
I don't know really what the goal was when Harlan started writing it, but that's been for me the goal in contributing to it. Really getting to dive in and see what it takes to make these features that look cool on paper actually come to life.
And can you tell us more about the history of the genesis of this language?
I really don't know.
It's really something you jumped into.
So Harlan had started working on it after he'd interned on the Swift team. And then I met Harlan at the Playgrounds Conference in Melbourne, Australia.
Some Australians in the room.
He was showing it to me, and I started writing some Trill, and there was a feature that I tried to use, and it didn't exist. So I said, okay, well, why don't we just add this? And I sort of repeated that, and eventually got to adding in stuff like string interpolation, which is a parsing nightmare, I promise you. And yeah, it just came from what language features do I want to see exist, and then going and adding them.
And what about you, Nick? Was it also just for understanding things, going deeper, or do you have yourself some real use cases and real usages for this parser?
So, I've always had kind of an interest in parsers ever since university, but the first time I actually sat down to write a real Swift parser that used these techniques was for Swift format. And that was basically, okay, so the problem I had was that we had a really messy code base, and at the time there weren't really any good options for auto-formatting Swift code. So I thought, I'll just write one, how hard can that be? And so I sat down to do it in Swift, and I had a few false starts, but I hit upon this particular approach that I've demonstrated here today, and it worked really well. And it's still using that in Swift format today. I mean, if I was going to write it now, I'd use libsyntax, which is, Apple provides now a Swift parsing tool that will give you all the tokens and AST nodes for free. But that didn't exist at the time. And since then, I've found many other times when I've either needed to or really wanted to write a parser using the same techniques. So my layout framework uses an expression language inside that uses this technique, and it's come up a few times.
And do you think those your two approaches, like trying to discover parsing or trying to discover how types is working with simpler use cases, would actually help people to dig into a real Swift language? And because I know a lot of people would really like to contribute to the language or to the tools, and it's really hard because the code of Swift is really complex, and it's even complex to just compile. And do you think that this could be a journey towards this goal?
I mean, I'd like to say yes. If you're not familiar with parsers and how they work, I think this is definitely a good way to learn that. Mm-hmm. In terms of actually helping you work on the Swift code base, the Swift code base is all written in C++, not in Swift, unfortunately. Yeah. And I mean, many people have complained about this, including the Swift maintainers. They wish it was written in Swift, because Swift is a much nicer language for writing parsers than C++. So, I've never contributed to the Swift source code base, even though I kind of understand conceptually how it works, because of all the compiling issues and so on that you're talking about. So yeah, this doesn't really help with that. I think it's much more useful to empower you to solve problems that you would otherwise just think, oh, there's no solution to this, or I have to wait for somebody else to solve it. So like the Swagger DSL that Jeffrey mentioned earlier, somebody at some point said, okay, it would be great if there was a language for describing network APIs. There wasn't one, so they created one. Yeah. And so this empowers you to do things like that, right?
Thinking abstractions.
Yeah.
Interesting. And in your case?
For me, it's more been about just satisfying my curiosity for figuring out how things actually work. I'm a big believer that there's no such thing as magic. People talk a lot about how there's magic ways of implementing things, or the phrase runtime magic came up a lot back in the Objective-C days. And for me, it's been about demystifying that and realizing that, well, this is all just code under the hood. And if it's code, that means I can write it too.
And do you think understanding what's below the compiler, or understanding more the typing systems, would make you a better developer on a day-to-day basis?
I think it does, but not directly. I think it's more about being able to, when I need to, understand what's going on. So if that's writing code and this code is slow, being able to have some intuition about where performance problems come from, or back in the Swift 1.2 days where you would get the Swift compiler would crash, being able to have some intuition about what your code, where the error was in your code that was causing a bad error from the compiler. It's really about being able to unravel all those things and not always have to jump straight to a tool that will provide the answer for you.
And that's why it's important to understand the concepts more than what it's actually implemented.
Yeah, likewise. I mean, it doesn't, for me, make it any less frustrating when Swift can't compile the code that I think it ought to be able to. But it's nice to have an understanding and think oh yeah, that's because that requires generalized existentials or whatever, right? Rather than it just being dumb compiler.
And do you know how it differs from the real parser of the Swift compiler?
So I'm not an expert, but name-dropping Harlan again, I thought you would ask this question, so I asked him, and he will confirm that the Swift compiler works in very much the same way, albeit C++, as the one we talked about.
Yeah, and the recursive descent parsing has some limitation, and in which cases it's kind of really tricky to use. And
so no, the nice thing about recursive descent is it's basically arbitrarily flexible. The problem with using...
It becomes slow in some cases, right?
Only if you have a lot of backtracking, which is down to the design of your language and down to the design of your parser. It can be avoided, it can be mitigated. But the key point I wanted to get across is, first of all, it's not scary to handwrite this stuff. And it's actually very simple code. And also, if you do handwrite it, it's very easy to solve those kind of problems. Whereas if you're using some kind of formal language for describing your parser, if you run into a case where it's pathologically slow, often there's not much you can do about it because it's just inherent, like that language only supports this kind of parser or this kind of language.
It's also a lot harder to create a really great user experience. So one of the things I've found is adding good error messages to a parser that uses like a parser generator or parser combinators is really, really hard. But when you write a recursive descent parser, you sort of know, like, oh, hey, I saw a quote, so I'm expecting to see an end quote, and if I don't see one, I can tell you that, versus just saying your program's invalid.
Yeah, you have much more context that you can actually give back.
I had the mic, but sorry. How much of your work is actually inspired by reading the Swift code source? The Swift compiled code source. I mean, especially in the trial case, did you get to do the solution yourself and then you compare the two, or you get inspired by what you read on the code base?
So I let Harlan do all the research for that. He's much smarter than I am and much more experienced when it came to compilers. But when it came time to implement runtime features, actually I just downloaded libobc and was looking at like how does the Objective-C runtime handle deallocating objects, and like where does dealloc get called, and how do you make it so you can call methods from inside of dealloc without everything yelling at you because you have a deallocated object and you're calling methods on it. So looking at prior art for all that stuff has been very helpful, although it can actually make things a bit more confusing, because these are all things written by experts. They're written by people who know exactly what they're doing. And sometimes that means they don't always communicate the structure of what's going on. It's just a bunch of code rather than having an overview of this is how this feature works conceptually.
Yeah.
Yeah, and, about having experts writing the language and deciding where the language is going. By the way, we're going to have a talk around that this afternoon, but and to come back to existential types, don't you think that there's a risk of getting the Scala symptom, like having a language that is so meta that it's really hard for developers to actually understand the language, and especially newcomers to the language?
I think that's definitely a risk, but the Swift team has made it clear, since they open source Swift and started talking about some of their philosophy behind it, that one of the things they really care about is this idea called progressive disclosure. And that's the idea that if there is a feature in the language, you don't need to know about it until you start to use it. So there's been talk of adding like a Rust-style borrow checker to Swift. And they said for them to do that, it would have to be opt-in. You're not going to have to learn how this thing works to write a Hello World program. And I think that's incredibly important, not only for newcomers to the language, but also general developer productivity. I think being able to write a snippet of code and have it compile and have it do what you expect from memory is incredibly important, because there are lots of times when like a colleague will ask you a question and you want to write up some code to like explain what's going on. And to be able to do that from memory without having to open up an IDE, without having to deal with a lot of errors, is a huge boost for productivity.
Speaking for myself, I mean, I have no functional programming background at all. I'd never used a functional programming language prior to Swift. And when I came into it, I started like a lot of people. I just treated it like an object-oriented programming language. And it lets you do that. It doesn't get in your way if you're trying to do that. But it's very good at slowly introducing into these functional concepts. You just add like a map here and a flat map there, and all of a sudden you're a functional programmer, and you're like, why doesn't it have like existentials? Like I need these features from like people keep telling me how great they are. So like I I don't think Swift is going to go down the route of suddenly becoming this like incomprehensible functional language that only PhDs can understand. I think it's actually a very gentle introduction to the world of functional programming. It kind of like whets your appetite for it.
Yeah, I'm not going to ask if Swift is actually a functional programming language, but
well, functional programmers would say no, and object-oriented programmers would say yes.
Yeah, that's the problem. And to come back to the parser ID, I was thinking something really cool that could be done, but I don't know if it's possible. Is to take this AST representation and kind of plug that into LLVM. I know that probably you'd still have to bridge the gap by writing something that goes from the AST and generates some higher representation. But do you think it could be feasible?
I mean, that's basically what Trill is. So, we deliberately didn't overlap our talks, but what I showed you here is the front end of Trill. Like, it wasn't deliberate, but that's how Trill works. And the back end is LLVM. So, yeah, if you want to see how to glue what I've written to LLVM, have a look at the Trill code base.
Nice. And the Trill code base is readable. Like, anyone could jump into this code base without like spending weeks reading it.
Yeah, it's written like normal Swift code. It's not like C++ template.
I know.
Nastiness. It's not super functional. It's just sort of normal, object-oriented code that takes advantage of like switch statements and stuff like that, and optionals and throwing functions. But so the one piece that's missing in between like writing a parser and generating LLVMIR is, funnily enough, the part of programming languages that we often spend the most time talking about, and that's called semantic analysis. So that's when you have an AST and you try and understand what that AST actually means. So that's like when types have actual meaning. For your language, it probably would be pretty easy to just go straight to generating LLVMIR or even machine code because the semantics of the language are so simple. But most compilers have that extra phase in the middle, which is is like understanding the types and figuring out what, inferring types and what function call you're actually calling, stuff like that.
Yeah, I mean, I didn't go through the interpreter code, but you can look at it in the repository linked, and that has to deal with this kind of issue. So it's simple enough in the case where you just have a plus operator, but when you've got a times operator, like what happens when you have a string times a string? That's meaningless, right? You can't concatenate in that case. So that needs to be a runtime error, which gets thrown by the interpreter. And if it was, if you were writing a proper compiler, that would then have to be like a different kind of error, an error produced in the sort of the type analysis phase, which is a phase that I didn't really talk about. One thing I would say though, like if you don't feel like learning C++ and like getting your head into LLVM, a very straightforward way to make something like this compile to native code is you just transpile it to Swift, which is a string, and then you pass that to the Swift compiler.
Yeah,
I mean, it's a little bit slower, but the end result is the same.
Yeah, that's actually a great way to start off with compilers. In that way, stuff like SwagGen is actually a compiler. So if you've ever done any sort of code gen tool, you've basically written for yourself a compiler. And that's why I find all this stuff to be so useful is, sure, maybe some of the techniques are a bit abstract and a bit heavyweight, but being able to dive in and have computers essentially write code for me, that's the dream, isn't it?
Yeah, definitely. And so what about the difficulty into integrating LLVM compiler? There are lots of languages who are using that nowadays, like Rust or Kotlin. And
So the first two words in LLVM are low level. And they're not kidding. LLVM is a great abstraction. It's really geared towards like implementing a C compiler. It's not the easiest thing to dive into. You end up writing like a bunch of when generating LVMIR, there are a bunch of casts, and like you have to know, like, are these int32s or int64s? Are they signed or unsigned? There are no string types in LVMIR, so it really is low level. Harlan, Robert Woodman, and myself maintain a library called LVM Swift, which attempts to give Swift bindings to the LVM-C API. But even with that, it's still a huge jump to go from like writing an interpreter for something to generating LVMIR.
I didn't know about that. Is it still maintained? Is it actively maintained?
That's a loaded question.
I think I've gotten GitHub notifications for it recently.
Yes. Yeah. Very good. Do you have more questions?
I think we're good.
That's good, actually.
Yeah, it was great. Like, thank you very much, gentlemen, for your 2 talks. And I think it's time for the break.